Let us start with next lecture, that is about gas laws. Now, the behavior of gases, it can be studied by variables like pressure, volume, temperature, and number of moles. So these are the four variables, 1, 2, 3, and 4, which will help you to study the behavior of gases. And these variables and measurable properties of gases, they are related with to one another through different gas laws. That's how do they relate to one another, and that is expressed by gas laws. Is how this pressure is related to this volume, how this volume is related to temperature, and all these variables like pressure, volume, temperature, how do they relate to this number of moles? If you combine the interrelation between all these variable properties, and that is expressed by different gas laws. Now, the relationship between this pressure, volume, and means number of moles, and temperature. These are summarized by 5 gas laws. The first one is Boyles Law. Second one is Charles Law. Third is Boyles Law. This thing we studied in basic concept of chemistry also. This is just the elongation of that law which we studied in that chapter. And next is Avogadro law. And the fifth one is Dalton's law. So this 1, 2, 3, 4, and 5. These laws are named after the scientists, different scientists. So first we'll talk about this Boyle's law. In this lecture we'll talk about Boyle's law. Now gas laws are based on the experimental observations made by the scientists. And these gas laws have played significant role in the development of chemistry. So the first one we'll talk about this Boyle's law. Boyle's law or pressure volume relationship. This is PV relationship, that is pressure volume relationship. So this law tell you about the relationship between pressure and volume. Remember, always you remember when you talk about the Boyle's law, it is always the relationship between pressure and volume. Now, the Robert Boyle carried out number of experiments on various gases, and he observed that at constant temperature. So this is important. When you talk about Boyle's law, the temperature is always constant. At constant temperature, when the pressure was increased, the volume of the gas was reduced. Okay. So when there is an increase in the pressure, volume is reduced, and vice versa. So when you write the Boyle's law, there should be no confusion at all. This Boyle's law, it happens at constant temperature. This is the necessary condition for Boyle's law. When pressure is increased, volume is reduced, and vice versa. Means when volume is increased, pressure is reduced. Okay. So the statement of this Boyle's law you can write, for a fixed mass, when you say fixed mass means number of moles. Okay, number of moles, that is M, of a gas at constant temperature. At constant temperature, the pressure of gas, pressure P of a gas is inversely proportional. is inversely proportional to the volume, V of gas. Okay. So it means that when pressure is increased, volume is reduced. Means there is an inverse relation between this. Or another way, you can write the same law as at constant temperature. Either of the statement is correct. At constant temperature, pressure of gas or pressure of fixed amount. When you say fixed amount, it is always related to the number of moles. Pressure of fixed amount of a gas varies, means changes, varies inversely with its volume. One and the same thing. You can put it in two different ways. Okay. So it means that pressure is inversely proportional to volume. This is nothing but the gas Boyles law at constant temperature. You just remember this. There should be no confusion between Charles law and Boyles law. So this is about the Boyles law. Now mathematically, how can you express this Boyles law? Mathematical expression, I just wrote it the same way. You can write pressure is inversely proportional to volume at constant temperature and any number of moles. So these are the necessary conditions. So you can write pressure is equal to K1, that is a proportionality constant, into 1 by V. Now on rearranging this equation, you can write PV equals to K1. It means that at constant temperature, product of pressure and volume of the fixed amount of gas is constant. When the product of this pressure and volume at constant temperature, this is always a constant. This is the proportionality constant. Means this thing can be put in a sentence in this way: at constant temperature, product of pressure and volume. Product of pressure and volume of fixed amount. This is also important. This fixed amount word. Fixed amount of a gas is constant. It's constant. This is the constant. Okay. So when a fixed amount of gas at constant temperature occupying volume V1, means if this is the V1 at initial pressure P1 undergoes expansion or compression. So if this is V1 is the initial volume, P1 is the initial pressure, so it changes to V2 and pressure P2. So according to Boyle's law, you can write P1 V1 will be equal to P2 V2 equal to constant. Okay. Means if you consider this at pressure P1, if this is the V1 is the volume of the gas, and if you change the pressure, accordingly volume will change, and the product of this P1 V1 will be equal to P2 V2, which is equal to constant. This is nothing but it's applicable to this equation. When you say PV equal to constant, means P1 V1 will be equal to P2 V2, and that will be equal to constant. Now this law can be represented graphically also. Now the graphical representation of this, there are three different ways you can put this graph. The first one like this: volume. This is plotted against pressure and volume. Pressure on the y-axis and volume on the x-axis. You will get such type of curves like this at different temperatures like T1, T2, T3. Means at this particular temperature, this temperature is constant. So as the volume is increased in this direction and pressure is increasing in this way, So you'll get such type of graph here. Means if you take one of the point on this here, if this is particular volume of the gas and this is the pressure of the gas. Now, if you go for this point at this graph, this is the volume of the gas and this is the pressure. Here. This is the value for the pressure. Here. Now, if you take third point here, this will be the volume and this is the pressure. Means what do you observe from here? That as the pressure increases, pressure is increasing in this direction. So the volume is increasing in this direction. As the pressure increases, the volume is decreasing. Here there is a less value for pressure at this point, for this particular point. So as the pressure is decreased, this volume is increased. So as we said that pressure is inversely proportional to the volume. So this is proved by this graph here. Now this is for one temperature. If you take at another temperature, you will get the same. The nature of the curve will remain the same. Means as the pressure increases, volume is reduced. That can be proved by this graph here. By taking such points here, you will be very easy to observe that. You will be easily observing that this is true for this particular graph. Okay. Now the second graph you can plot this way: pressure on the x-axis and product of pressure and volume. We know that this product of pressure and volume is constant. We are seeing this thing in the earlier equation. This pressure, product of pressure and volume, it is constant. So here, if you plot this graph for different temperatures, you will get such horizontal lines like this. So this also proves that even though there is an increase in the pressure, the product of this pressure and volume, it will remain constant. Okay. It means that what are these three different lines? This is the different temperature. Means even though if you are changing the pressure, there is no change in this product of this pressure and volume. At any temperature, the volume would remain same for this particular temperature. Of course, the temperature should be constant. It means that. Third way, you can graphically represent this graph. That is inverse of volume is plotted here on this x-axis. Reciprocal of volume is if you take, then pressure on this y-axis. So at different temperature, you will get such type of graphs. Like this. The nature of curve graph will be like this at different temperature. Means for this particular line, this straight line passing through the origin, temperature is constant here, and this is nothing but a reciprocal of this volume. So this is the first graph where the pressure versus volume is taken. So in this first one and the third one, the difference is that we are taken the reciprocal of volume, inverse of volume rather, 1 by V. Okay. Here there is only V. So there is change in the nature of the graph here. Is if you just inverse the volume, and if it is taken increasing in this direction, and the temperature is being kept constant for this particular graph line here, which passes through the origin, this is the nature of the graph. So in this way, when the pressure of glass is plotted, a straight line is obtained passing to the origin, provided that temperature and, of course, in all the three cases, the temperature and number of modes should be kept constant. Okay. Now, this is the graphical representation. You always remember all these three types of graphs, and you just focus on what is taken on the x-axis and the y-axis. This is important, and everything should be labeled here. Now, the next is Boyles Law in terms of density of gas. Boyles Law in terms of density of gas. Density of gas. Okay. So with increase in pressure, gas molecules get closer and the density of the gas increases. Means if you increase the pressure, right here, with increase in pressure, what happens? The gas molecules, they get closer. Gas molecules will get closer to one another. Gas molecules get closer, and what is the result of this? And density of the gas increases. Okay. So at constant temperature, we're talking about Boyles Law. So the temperature is constant. At constant temperature, pressure is directly proportional to density of fixed mass of gas. Okay. So at constant temperature, pressure is directly proportional to density of fixed mass of a gas. Now we know this equation P V equal to K1. Therefore, we can write in terms of V, V will be equal to K1 upon P. We are just rearranging the equation. But we know that from this thing, we can write, then we know that density equal to mass upon volume. Okay. Mass upon volume. Okay. Now, if you substitute here, density equals to mass upon volume. Now, this equation, if I number this as equation number 1, this is your equation number 2. Now on substituting V, you can write this V will be, if you rearrange this, D equal to mass upon volume. So in terms of D, we can write D will be equal to M upon K1 into P. What did we do? We just wrote this equation in terms of P because D is equal to mass upon volume. So we can write V will be equal to M upon D. Okay. Now this just if you write this V equal to M upon D, I'll write here M upon D is equal to K1 upon D. Okay. So we can write in terms of density. Density will be equal to M into P divided by K. So this is the same thing I wrote here. I just tried to make it simpler for you. So if you can write this way also or this way also. You can write directly this equation, and if you find it a little difficult, you can write this way also. So this now we can write D is equal to K dash into P. What is this K dash? K dash is nothing but new constant. This is K1 we got from here. So this M upon K1, because this M, the mass of this substance should be constant, fixed mass of the gas. We have already described this condition that the mass of the gas should be constant. So this whole thing will become constant. So for this M upon K1, we can write new constant, that is K dash into P. So you can write, therefore, D is proportional to P. So this Boyles Law can be written in terms of the density also. So this above equations show that at constant temperature, I write here somewhat here. At constant temperature, this equation, I am talking about this equation. At constant temperature, the pressure is directly proportional to density of a fixed mass of a gas. So this is about the Boyles Law. So I'll give you some problems based on this in the next lecture.